sum of a bunch of functions, each of which are cosines. So there's the first part here. Okay, cosine of something. I'll just put the pi in here just for fun. Okay. And what I'm going to do is I'm going to let this sum go from n equals, doesn't matter here what it starts at, 1. Okay. And it's going to go, well, I'm going to let it go to something here. Okay, you have to guess what. I'll give this thing an amplitude, but I will raise it to the nth power. Not an amplitude, sorry, this affects the frequency, right? Then I'll give this thing an amplitude, and I'll raise it to the nth power. And now what? What am I adding up? Well, these are a bunch of cosine functions, right? So they're wavy like this, yes? But as n grows, they get what? Higher frequency. And, well, taller or shorter depending on, well, I haven't told you what A and B are, so I have to tell you, actually, don't I? So I'm going to let B be between 0 and 1. We'll fix B between 0 and 1. And I'll let A be an odd integer. Okay. And I'll choose A and B so that together their product is bigger than 1 plus 3 pi over 2. Okay. This product has to be big enough so that this thing, as it gets more jagged and thinner, it doesn't suddenly, if this weren't true, the thing may not look like this in the limit. Okay. Okay, good. So it's about sum of a bunch of cosines, and then what? How many of them should I add? If I add only finally many of them, this is just the sum of continuous functions, which is continuous, right? So here's the thing that the big kicker that makes this thing way more interesting. It's a sum of a bunch of, it's an infinite sum. Okay? So point-wise, this is a series. Okay? But as a collection of functions, it's an infinite sum of a bunch of functions. And of course, you can't say, as we'll see, that the infinite sum of a bunch of continuous functions is necessarily continuous. We have no theorems like that yet. Okay? Yet. Okay? Analysis 2. Okay? We start talking about sums of continuous functions. Actually, I'm going to say more about this next week, just to give you a hint of what's coming in analysis 2. But let me show you what the picture then looks like. So, the first function looks something like this, right? And then on top of that, you add a second function, which has a higher frequency and also smaller amplitude. So you're basically adding a sine, a wavy function on top of a wavy function. So it looks like this, yes? And then the third stage, you're adding something that's a little more, has a higher frequency and smaller amplitude. So you're basically adding up a wavy function that's has a little more amplitude, yeah?
So what you're drawing is what it looks like after you sum the third term.
Yeah, I'm showing you the partial sums of this sum of continuous functions, okay? Good, and then the fourth one, I'm not going to draw, but you can imagine is basically going to add a little more jaggedness. And the claim is in the limit, because this is a limit of a bunch of partial sums, you'll get something which happens to be verifiably continuous. I'll show you how to verify that next week, okay? But also verifiably not differentiable, okay? Kind of a very cute function.
Can that function essentially be described as a fractal function in some way?
Yeah, I mean, this is.
That's how you can get a lot of properties out of that. I feel like.
Yeah, I mean, if we haven't defined what a fractal is, but this, if anything's a fractal, this certainly is. Yes. definitely. Okay, very cool. So what I want to do after the break is I want to show you a theorem, which is probably the most important theorem about derivatives, and that's the mean value theorem. Okay, so let's take a couple minute break.